Afternoon. All right, so like I was saying, Chemistry 3111, we left off not completing this question last class. So you can see there is not a plane or axis of symmetry in this compound. And so there's going to be two different resonance stabilized carbocations that we can form here. So what I'm going to do is I'm going to start by drawing one, because the question asks us to draw, it says predict the products for each of the following reactions and propose a mechanism that explains the formation of each product. Okay, so I'll do the first Markovnikov addition, which is going to look like this. Okay, and again, it's not really a Markovnikov, it's more about forming a resonance stabilized carbocation, but you'll see that clearly once I draw the carbocation, which is going to be allylic. So we have these two methyls, we didn't touch those, and now we have a positive charge here. And you can see that you have an allylic carbocation, so we can draw a resonance form for that. So I'll just put in a resonance arrow, and I'll put in my brackets like this, and we'll draw the resonance form that results, which looks something like this. So we'll have the positive charge up here now. And there you go. So those are the first two resonance forms. I'm going to delete the resonance arrow just so I don't have to redraw everything a million times. And now what we're going to do is we're going to draw the result of the nucleophilic attack of the bromide onto the carbocation. And remember, the carbocation is sp2 hybridized, so therefore it's trigonal planar. So that means the nucleophile, the bromide, could attack from either face of the molecule. It's going to be indiscriminate. And so when we draw our products, we're going to be sure to write that we're going to get a racemic mixture. So we're going to end up this compound. And of course, this is a stereocenter. So I'm just going to write racemic. Okay. And then we're going to write the product of the next one. So let's draw a product of that nucleophilic attack, which is going to look like this. Okay. And of course, this is a stereocenter. And so that will be racemic as well. Now, hopefully I won't run out of space here. But what I'm going to do is I'm going to copy this part of the mechanism, okay, just the reagents really. I'm going to copy it and I'm going to paste it down here, okay. I'll paste it here and I'm going to put it in a different color so we don't get the two confused, okay. And I'll delete my curved arrows that I put in here. So now we're going to form the other resonance stabilized carbocation. So we're going to add the hydrogen here to this carbon. And so let's draw the product of that. So that's going to look something like this, where we'll have the positive charge here. We have our geminal dimethyl. We have our double bond, and we have our methyl group here, okay? And we can, of course, draw a resonance form for this. Let me just move it over here. There we go. So now we're going to draw the resonance form for it. I'll use my red arrow again. There we go. Let's draw the resonance form. Just going to look like this. Oops, I can fix that bond. Make it a little prettier. There we go. We have our positive charge up here. And there we go. Okay, so those are our two resonance forms. Again, I'm going to delete the curved arrow just so I don't have to redraw everything over and over. And then the result of the nucleophilic attack of our bromide, I'm not going to draw the lone pairs in this time, just to make things a little easier on myself. I'll draw this, and let's draw the two products that result. So we end up with something that looks like this. Okay, so we have our gem dimethyl. There we go, and we're going to have our bromine here. And keep in mind that this is racemic, right? Because it's going to attack from either face of this carbocation. And then finally, we'll draw the last product, which is going to look something like this, where we have our bromine here, our methyl group here, and our two methyl groups like this. And of course, this is going to be racemic as well. So if you're confused as to why do you write racemic every single time, why is it that you're writing racemic? Well, every time the mechanism, we have a nucleophile attacking a carbocation, and we know that carbocations are trigonal planar, and so the nucleophile is going to attack from either face of the molecule. Okay, it's not going to discriminate whatsoever, and so we end up with 4 racemic mixtures. And if you're wondering, is that a total of 8 compounds? Yes, it is. So you end up with a total of 8 products. 8 different products. Okay, 4 racemic mixtures, products, no matter how you slice it. So is that a lot of products? Oh yeah, that's absolutely a lot of products. So you might be wondering, is there a way we could minimize the number of products that are formed? And that's going to bring us to the next part of 16.5, okay, which is right here. Okay, so this is the question that we just solved. It's 16.6c. So we've completed 16.6b. You see, we did the first part here on Wednesday, and then we did the second part here. Okay, so now we're still in the same chapter. We're still in 16.5, but now we're going to talk about that 1,2 adduct and that 1,4 adduct, or the product of 1,2 addition and 1,4 addition. So take a look at this compound here. Again, this is called 1,3 butadiene. The reason I keep mentioning the name is because this compound shows up, I think, Avogadro's number of times in this chapter. Okay, so if we were to add the hydrogen, if we added this hydrogen here, okay, or here, and then we add the bromine here or here, well, you can see that this one we call it the 1,2 adduct for a reason, and this one we call it the 1,4 adduct for a reason. And so it turns out that we can actually affect the ratio of 1,2 adduct versus 1,4 adduct. And here's how we do it. If you do the reaction at low temperature, so this is low temperature, 0 degrees Celsius, low temperature, you actually end up getting mostly the 1,2 adduct. Whereas if you do it at 40 degrees Celsius, which might not seem like a very high temperature to you, but it's high enough that it switches the ratio. Now we get mostly 1,4 adduct and very 1,2 adduct. Now we have names for these two products besides 1,2 and 1,4, and I'm going to get to these in a second. But the 1,2, we call it the kinetic product, and the 1,4, we call it the thermodynamic product. Okay. Now, if you're, man, I used to know all about kinetics and thermodynamics, but now I don't think about it as much. Well, let me remind you, kinetics has to do with rate. How much time does it take for the reaction to occur? Whereas thermodynamics has to do with stability. Which one of these is the most stable? Well, hopefully you can see that the 1,4 adduct is the most stable product because the alkene is disubstituted, right? It's attached to this carbon and this carbon. So it is disubstituted, whereas the alkene in the kinetic product is only monosubstituted. It's only attached to one carbon. So that will help you a little bit in thermodynamics, and I'll explain kinetics in just a second after we look at this reaction coordinate diagram. So to kind of put more detail on what I was just saying, the 1,2 adduct forms faster, and so we say it's the kinetically favored product. So 1,2 adduct is the kinetically favored product, and then the 1,4 adduct, that forms more slowly, and it's more stable. Okay, maybe I shouldn't even say slowly, it's just more stable. Okay, and we call that the thermodynamically favored product. So take a look at this potential energy diagram here, this reaction coordinate diagram. You might think it's kind of boring to look at this, but look, it shows you everything. All the answers are in here, right? The first step to form the 1,4 or the 1,2 adduct, they're the same, right? Up to this point, they're identical. It's just a proton transfer to form an allylic carbocation. So now the whole idea is, well, where is the nucleophilic attack going to occur? Is it going to attack here at this carbon, or is it going to attack at the resonance form like this? And you can see that the one that I just drew leads to the 1,4 adduct, and this one over here leads to the 1,2 adduct. So what gives? Well, again, the nucleophilic attack is going to be more rapid. There's going to be a lower activation energy to make the 1,2 adduct, right? It's kinetically favored, right? Lower activation energy equals faster rate, right? Nothing new there. Like now it's coming back to me. Good, okay? So lower activation energy, therefore a faster rate. But if we look at the potential energy, you see that the 1,4 adduct is more stable, right? Lower potential energy, therefore more stable. So it's a battle between the two. It's a battle between reaction rate and stability of the final product. So how do you control them? Well, it's with temperature, right? It's with temperature. So it says here the 1,4 adduct is more stable. Why? Because it's the more substituted alkene, right? In this case, you see that this is disubstituted, whereas this one here is mono-substituted, okay? So the 1,4 is going to be more stable. So it says here that at higher temperatures, the formation of the products is equilibrating, right? And so the reaction is under what we call thermodynamic control, and the major product is going to be the more stable product. Okay, again, if you do it at high temperature, you have enough energy to go over this and then to go back again and then to go up here. And then eventually everything is going to find its way down here to end up being more stable in the end, because this part is going to be reversible. Whereas when we make the 1,2 adduct, it actually forms faster because of something called the proximity effect. And you're like, proximity, that would mean closeness. Yes, 1 and 2 are closer together than 1 and 4, aren't they? Yeah, absolutely. So once you form that carbocation, that allylic carbocation here um, after your proton transfer, the reason the kinetic product, the 1,2 adduct, forms faster is because the bromide is going to be right next to the positive charge at carbon number 2, and it just forms faster. That's it. That's the whole answer. It's not any more complicated than that. Now, I'm not going to ask you to write an essay on this or give me some kind of Shakespearean soliloquy on this or something like that. All I really need you to know is this. Is at low temperature, the kinetic product, at low temperature, the kinetic product is going to predominate. I can find my slide again. Oh, these days. There we go. What I need you to know is that at low temperature, the kinetic product is going to predominate, and at high temperature, the thermodynamic product is going to predominate. I need you to know that the kinetic product is the 1,2 adduct, and the thermodynamic product is the 1,4 adduct. As long as you can remember those, you'll be in the clear for most everything that we ever do with kinetic and thermodynamic products. So here it says predict the products for each of the following reactions, and in each case determine which product is going to predominate. Well, here you can see we did the reaction at 40 degrees Celsius. And so if it's 40 degrees Celsius, that means the thermodynamic is going to predominate, and that is the 1,4 adduct. Before I get to that, look at the next question. It's 16.9b. It's the same question with a little bit different substrate, but now you're doing 0 degrees Celsius. And so when we're at 0 degrees Celsius, it's going to be the kinetic product that is going to predominate. And remember, that's the 1,2 adduct. Okay, we're going to draw both, and then we're going to just say which one is the major product. Now, the cool thing about this problem is you can see there is an axis of symmetry in here. And so you don't have to draw a whole bunch of different proton transfers. There's only one that's going to be relevant. And so let's draw our HBr molecule out explicitly like this. So we're going to get our proton transfer, and we're going to form our resonance stabilized carbocation. So we're going to form something that looks like this. Okay. We're going to have a carbocation here. And there you have it. Okay, so that's an allylic carbocation. So let's draw the resonance form, which is going to look like this. So we're going to draw our curved arrow like this. And we're going to draw the other form. Here we go. So that's going to look something like this. Now keep in mind that this proton, and I'm doing this for instructional purposes, I'm your teacher, okay? So keep in mind that the proton from your HBr is this one here that I have labeled in green. So you would call that carbon number 1, the carbon it's attached to. So if I put, oh, I forgot to put my square brackets. So let's fix that. Square brackets for my resonance structures. So now what's going to happen is we're going to draw the product of the nucleophilic attack. So we're going to have our bromide ion. And we're going to draw another bromide ion here. And you certainly don't need my help to draw this curved arrow. We're going to end up something like that. Keep in mind that both of the products in this case are going to be racemic mixtures, right? Because the carbocation is sp2 hybridized. But anyhow, so let's draw the first product, which is going to look like this. So we end up with something that looks like this. So we have our double bond here. Now our bromine is going to be right here. There we go. And then this product is going to look something like this. So we've got our 2. There we go. All right. So which one would be the 1,2 adduct? Would that be the one on the left or the one on the right? The kinetic product. Which one would be kinetic? Is it the one on the left or the one on the right? Anybody? Kinetic product. So keep in mind the kinetic product is the 1,2. Yeah, it's the one on the left. Absolutely. Absolutely. So this is the 1,2 adduct. And therefore, this is the kinetic product. This one is the 1,4 adduct. And therefore, this is thermodynamic. So
Is the when it's served by itself, is it the same size that comes out with the sandwich?
Sorry, can you say it louder? I can't hear you. Sorry, Siri's listening to me. Oh, sorry, whoever has their mic on, I can't really hear your question. Anastasia, I can't really hear your question. Did you have a question? All right, so let's go back here. All right, so we're looking for the thermodynamic product, and clearly you can see that this is the thermodynamic product, and so this will be the major product. Major product, and of course this will be the minor product. Another thing you probably notice is that the alkene in the thermodynamic product is tetra-substituted, but in the kinetic it's only tri-substituted. So there you go. So that's a little practice on that. Let's try the next one. And again, I'm sure you don't need my help with these, but let's just try it anyway. We'll go a little quicker this time. So now we're going to draw the resonance stabilized carbocation, and we're going to say that the 1,2 product will be the major product. Why? Because we're doing the reaction at 0 degrees Celsius. So I'll draw my HCl molecule like this. We'll do our proton transfer like this, and we end up with a resonance stabilized carbocation. Just going to look like this. Okay, so let's draw the resonance form. So we'll put in our resonance arrow like this. Go. So we're going to end up with this carbocation like this. Keep in mind that the proton that we added was here. Okay, that's this proton here. And so now let's draw the product of the nucleophilic attack by the chloride ion. I'll just put Cl minus, Cl minus. And so the chloride is going to attack here. This chloride is going to attack here. And due to the proximity effect, the product that I'm drawing right now, the one on the left, will be the major product. So there's our chloride. Fix that a little. There we go. Something like that. And then over here, we have the 1,4 adduct, which is, of course, our thermodynamic product. And so that's going to look something like this. Keep in mind that this will be racemic and this will be racemic, but this is the 1,2 adduct. And this is the 1,4 adduct. So this one is going to be kinetic. And this one will be thermodynamic, like that. And so in this case, since we're doing the reaction at 0 degrees Celsius, this will be the major product, and this will be the minor product. And there you go, my friends. That's it. We're missing a methyl group. Yeah, I'll throw it in there, Kristen. I was just testing you. There we go. Better?
Yes, thank you.
Thanks for letting me know. Good. If I leave anything out again, just let me know. All right, so that covers section 16.5. A little bit about it's kind of like, I don't know. I mean, thermodynamics and kinetics is something that I guess you learn in general chemistry 1. It comes up a lot in general chemistry 2, because you do a whole chapter on reaction rates and rate laws. Then in organic 1, we talked about thermodynamics and kinetics again. And now, you know, it's rearing its ugly head again in organic chemistry 2. So you really can't get away from the idea of kinetics and thermodynamics. But I digress. That brings me to section 16.6. Don't stress about this section. It's just an introduction to what we call pericyclic reactions. Pericyclic reactions is a big subject, okay? There's really only one kind of pericyclic reaction we study in this class, and it's the Diels-Alder reaction. Okay, there are others that are in the textbook. Yep, absolutely. But the only one that you need to know is the Diels-Alder. And this is a representation of the Diels-Alder reaction actually here. This is, I'll just abbreviate it, the DA, the Diels-Alder. And what's cool about this reaction is that it's concerted. If you don't remember what concerted means, it means that all of the curved arrows for the mechanism are all drawn at the exact same time. So if I redraw the 1,3-butadiene like this, and if I redraw the ethylene like this, you might wonder, well, this way the arrows are kind of drawn going clockwise. Could I draw them going counterclockwise? Would I get the same thing? The answer is absolutely. If you draw them counterclockwise like this, you still get the exact same thing. So you notice that you ended up breaking two pi bonds and forming two sigma bonds net, right? You notice that you have two pi bonds that aren't here anymore, and then you formed two sigma bonds that weren't there in the initial starting material. So that is what the Diels-Alder reaction is. And like I said, you know, the reason why they won a Nobel Prize for it is they made a carbon-carbon bond here and they made another one here. They made two carbon-carbon bonds simultaneously. So yeah, way to get famous quick as an organic chemist. So as far as electrocyclic reaction goes, I'm not going to test you on this. I'll just leave this as an FYI. But you can see that this is another type of concerted mechanism. In this case, we end up gaining a couple of sigma bonds overall, and we lose a pi bond in the process. And then this one here is a sigmatropic rearrangement. I'll leave this one as an FYI as well. I'm not going to test you on that. So again, the only one you need to know is going to be the cycloaddition, and the only type of cycloaddition we're going to study will be the Diels-Alder reaction. And again, the reason why we studied the Diels-Alder is because they won a Nobel Prize. So to summarize, like what this section is kind of telling you is that all of these pericyclic reactions, and this means the Diels-Alder reaction included, what do they have in common? Well, you notice the mechanism is concerted. That means that all arrows, all curved arrows are drawn at the exact same time. Okay, so you don't have to draw one step and then another step and then a carbocation. There's no charged intermediates. Okay, so the mechanism always involves a ring of electrons just moving around in a loop. The transition state is some kind of cyclic transition state. And there's no, you noticed that in that mechanism that I drew, there was no carbocations, no carbanions. And so solvent doesn't really do a whole lot to your reaction rate because there's no carbocations or carbanions formed in there anyway. And so there's very little charge in your transition state. And so you can use all kinds of different solvents for these pericyclic reactions. So here's a bit of a summary of what I was getting at. The cycloaddition, which is again the one that we're interested in, the Diels-Alder is a cycloaddition. It involves the formation of two sigma bonds and the loss of two sigmas. Electrocyclic, you gain a sigma, you lose a pi, and then in sigmatropic, you don't gain or lose anything. It's just a rearrangement, so to speak. So here we go. Let's get into the Diels-Alder reaction. What I'll do is I'll just do kind of an introduction to it first, and then we'll take a short break to give you a little bit of time to think about it before we get into a whole plethora of practice. So here's the reaction. What we have here, you guys know this compound. I've shown it to you a few times already today, 1,3-butadiene. This is what we call our diene, and you can guess where that name comes from because it's got two alkenes in it. And then this portion right here with the one double bond, we call this the dienophile. Dienophile. And another way we can describe this reaction is a 4+2 cycloaddition, right? We have 4 atoms that are part of the transition state, and then we have these 2 atoms that are part of the transition state. You can practice drawing your curved arrows. I like to draw them like this, where I break the pi bond and then drag it through the carbon where the bond is going to be formed. And then I form my new pi bond, and then I drag it through this carbon to show that, you know, this carbon and this carbon are involved in forming the new carbon-carbon bond. So again, like I said, you can draw the arrows clockwise the way I have them drawn, or I can erase them and I can do it counterclockwise. So I could do it like this, or that's the way I did it, isn't it? You could do it like this, and like this, and like this. I had a counterclockwise, didn't I? Sorry, I'm confused. All right, so again, it doesn't matter. Okay, this doesn't matter one bit. And if you're wondering, does that only mean in our class? No, it means anytime you're drawing a pericyclic reaction, You can draw the ring of reaction, ring of electrons going in the clockwise or counterclockwise direction. It doesn't matter at all. It's good either way. All right. All right, so let's get back to it here. So here we go. All right, so let's take a look here. Here is the reaction coordinate diagram for the Diels-Alder. It's like, it's not that exciting, is it? Well, if you think about it, you know, pi bonds are weaker than sigma bonds, right? We lose 2 pi bonds and we gain 2 sigmas. So when we gain 2 sigmas, sigmas are stronger. And so it makes sense that the product of the Diels-Alder reaction is more stable than the starting materials, the diene and the dienophile. And you can see that the transition state, there's no charges anywhere in the transition state. So that's kind of cool too. All right. So here's something else that you might find kind of interesting is what we call a retro Diels-Alder reaction. I know about the retro Diels-Alder because I've been a victim of it a few times where I was trying to do a Diels-Alder. Okay, I set up my diene and my dienophile, put them in a reaction flask, heated them up, and I get the Diels-Alder product. But the thing is, if you heat it up too high, if you jack up the heat too much, it goes right back to your starting materials. And you might be going, what the heck? I thought if you heated it up more, shouldn't it just make the product faster? It's a nice idea, and we do have an explanation for it. So it says, most Diels-Alder, and I'm just reading off the slide, are thermodynamically favored at low and moderate temperatures, right? Remember, the product is a thermodynamic product. It's more stable than the starting materials. However, if you jack the temperature above 200 degrees Celsius, so if you go greater than 200 degrees Celsius, then it goes backwards and you get the Diels-Alder the retro Diels-Alder, because entropy, if you remember delta S, okay, that becomes the predominant factor instead of your delta H. So, and if you're wondering about the curved arrows going from here to here, it's just the same old curved arrows, right? You do something like this, and something like this, and it takes you right back to your diene and your dienophile. So I know you guys remember this chestnut, right? Delta G is equal to delta H minus T delta S. Okay, so remember, a sigma bond is stronger than a pi bond. You guys are fully aware of that. So we have to take into account the enthalpy term and then the entropy term. So let's take a look. So enthalpy term, remember, pi bond is being converted into sigma bond. We make something that's more stable, so we end up releasing heat along the way, and so we get a negative delta H. Son of a gun. We get a negative value for our delta H like that. All right, so now we have a negative value here. We're like, okay, that's good, right? Because we want our delta G to be negative, because when it's negative, it's spontaneous, right? When delta G is negative, the reaction is spontaneous. Okay, so let's think about our T delta S term. Well, T is in Kelvin, so it's always positive, right? T is never going to change. It's always going to be positive. So if we think about negative T times delta S, well, if our delta S is going to be negative, our entropy is decreasing. Why? Because we have 2 molecules coming together to form 1 molecule. So if you have a negative times a negative, you get a positive, right? If you take negative, and I don't need to coach you on this, but negative times negative gives you a positive, right? So if we have negative T times negative S, that means we get a positive term. So we're taking a negative overall and we're adding a positive. So when is delta G going to be a negative number? It's going to be a negative number when this positive number is small. And this positive number is going to be small. So we'll write here small at low temperature, but it's going to be large at high temperature. So if you jack up the temperature too high, it makes that number too positive, and then it's going to dominate over the negative term, and then you get a positive delta G. So that's why the retro Diels-Alder happens when you jack the temperature up too high. So this is just a summary of what I just told you. Okay, so I'll read it for you here. It says, for the Diels-Alder, enthalpy has to be bigger than the entropy term, the whole negative T delta S, in order for the reaction to be negative, right? Because when this is negative, it will be spontaneous, meaning it will give us the Diels-Alder product. But if you jack it up, if you jack up the temperature way too much, then it makes the entropy term too positive, and so it goes backwards. It gives you a positive delta G. So again, the ideal temperature for a Diels-Alder is somewhere between room temperature and 200 degrees Celsius. So there you go. Does that make sense to everybody? I'll put here very high temperatures. I'll just put greater than 200 degrees Celsius. Give me a thumbs up if you're with me on that. Cool, cool, awesome. There you go. So a little bit about Diels-Alder and the retro Diels-Alder. Let me just show you a couple more things before we take a short break here. But there's some other cool stuff. I already went over the term diene and dienophile with you, so you guys know the diene has the two alkenes in it, and then the dienophile has only one double bond in it, right? It's seeking a dienophile. Well, it turns out that in order to get the Diels-Alder to go well, the dienophile has to have some kind of electron withdrawing group. So I'll circle this X here and put EWG, which stands for excuse me, electron withdrawing group. What could it be? It could be a halogen, it could be a nitro group, it could be a nitrile, but you've got to have something electron withdrawing, otherwise the reaction doesn't work. In fact, if you just take 1,3-butadiene and you mix it up with ethylene and you crank it up, you can get cyclohexene, right? You can get it, but you see that your yield is very low. Low yield. So that tells you this reaction works, but it's not a great reaction, okay? So what are some of the electron withdrawing groups you could use? Well, I told you maybe a nitrile or a nitro, but one of the most commonly used electron withdrawing groups is something with a carbonyl on it, right? Because you guys know that when you have a carbonyl, you guys know there's a dipole because oxygen is more electronegative than carbon. And so carbonyls like this aldehyde make great electron withdrawing groups. In fact, if you do this reaction, you get a 100% yield. So very high yielding. Again, you could practice your curved arrows. You could say I form my 2 sigma bonds, make a new pi bond like that. So what are some of the electron withdrawing groups? Again, everything with a carbonyl, right? Whether it's a ketone, so this is a ketone, or if it's an ester, this one's an ester, or a carboxylic acid, or this one here, which has, a carbon with a triple bond to nitrogen, like this, which has a dipole. This is called a nitrile, if you don't remember that functional group. And so all of those make really good electron withdrawing groups, and so they all make excellent dienophiles. Now, what about the stereospecificity, or stereoselectivity, I should say, of the reaction? It turns out that the Diels-Alder is a stereospecific reaction, depending on whether your dienophile, which is an alkene, if it's E or Z. So you can see that if it's a Z dienophile, we end up with our two groups being cis to each other. And if we use an E dienophile, we end up with our two groups being trans to one another, like that. If you're wondering, well, come on, an alkyne also has a pi bond in it. Could I use an alkyne like this? Could I use that as a dienophile? The answer is absolutely. Okay, absolutely, right? You just draw the same old curved arrows like this, but now you're going to have two pi bonds, right? You're going to have two double bonds in your product like that. So now what we're going to do is we're going to take a short break, and I want you to try drawing the curved arrows for some of these reactions. Now, I'll just level with you. My students will sometimes struggle drawing the mechanisms when things are oriented like this. They like to redraw it, to put the diene like this, and then they'll draw the dienophile like this, okay? It will help them, maybe, oops, I can move this down just a hair. But this might help you when you're drawing your mechanism. Let me just spruce this pi bond up, right? Because then you can draw your curved arrows like this, oops, like this and like this, okay? Not my best work on you. There we go. Something like that, okay? We could practice drawing our curved arrows. And again, since we're starting out with an E alkene, when we draw our product, these two acyl groups should be trans to one another, right? So again, you're going to need, I'm going to write this in the notes, will need scratch paper. You cannot do these in your head. If you can, man, oh man, that would be amazing. You'd be like, what's his name? Who's the guy that was good at hunting? Matt Damon. Yeah, you'd be a genius like Matt Damon. If you could do that, my hat is off to you, okay? I couldn't. I like to draw everything out very carefully, but I want you to try all four of these, and then what we're going to do is we're going to come back and talk a little bit more about dienophiles and why some dienes don't work as dienophile, or sorry, we're going to talk a little bit more about dienes and why some dienes don't work well in Diels-Alder reactions. In fact, a lot of them don't work at all in a Diels-Alder. So I'll go over that with you. Okay,